According to the National Electrical Code, a new electrical service installation must be grounded. The code provides options for the grounding electrode system. The primary method is to connect to the building's water main. However, the National Electrical Code recognizes that not all buildings have accessible metallic water mains suitable for use as a grounding electrode. In such cases, the code permits the use of ground rods as an alternative grounding electrode system. Specifically, NEC Article 250.52 A2 outlines the requirements for using ground rods. The grounding electrode conductor must be connected to the grounding electrode system by connecting to at least 2 grounding rods. These rods must be driven at least 6 feet, that is 1.8 meters, into the earth. The rods must not be less than 6 feet, that is 1.8 meters, apart. Therefore, based on the information, 2 ground rods spaced 6 feet apart are indeed permitted as a grounding electrode system for the new service installation. However, there are specific conditions that must be met. Firstly, there must not be an accessible water main on the premises that can be used as a grounding electrode. If a metallic water pipe is available and meets the requirements of the NEC, it should be used as the primary grounding electrode. Secondly, the ground rods must be driven at least 6 feet into the earth to ensure they make adequate contact with the surrounding soil. Thirdly, the ground rods must be separated by a distance of at least 6 feet to provide effective grounding and reduce impedance. It is important to note that the National Electrical Code provides specific requirements for the size and type of grounding electrode conductor used to connect the ground rods to the service equipment. Consult the relevant sections of the National Electrical Code, such as Article 250, for detailed information on conductor sizing and installation requirements. Additional considerations for grounding electrode systems include soil resistivity, which can affect the effectiveness of ground rods. In areas with high soil resistivity, it may be necessary to use longer ground rods or additional ground rods to achieve the required grounding impedance. It is also important to ensure that the ground rods are properly bonded to any other available grounding electrodes, such as metallic building frames or underground metal piping systems, to create a comprehensive grounding system. Furthermore, consider local amendments or regulations that may supplement or modify the National Electrical Code requirements. Local jurisdictions may have specific requirements for grounding electrode systems based on local conditions or practices. Therefore, it is crucial to consult with a local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations. In summary, the National Electrical Code permits the use of 2 ground rods spaced 6 feet apart as a grounding electrode system for a new service installation, provided that there is no accessible water main on the premises. The ground rods are driven at least 6 feet into the earth, and the ground rods are separated by a distance of at least 6 feet. Always consult the National Electrical Code and local regulations for complete and accurate information on grounding requirements. Remember to prioritize safety and ensure that all electrical work is performed by qualified personnel in accordance with applicable codes and standards. The function of grounding is multifaceted, primarily serving to protect individuals from electrical shock and to safeguard equipment from damage due to overvoltage conditions. A properly installed grounding system provides a low impedance path for fault current to flow back to the source, causing the overcurrent protective device, such as the circuit breaker or fuse, to trip and to energize the circuit. This rapid clearing of the fault minimizes the risk of electrical shock and reduces the potential for fire or equipment damage. Grounding also plays a crucial role in mitigating the effects of lightning strikes and voltage surges. By providing a path for these transient voltages to dissipate into the earth, the grounding system helps to protect sensitive electronic equipment from damage. In addition to safety and equipment protection, grounding also improves the performance and reliability of electrical systems. A properly grounded system minimizes electrical noise and interference, which can disrupt the operation of sensitive electronic devices. It also helps to stabilize voltage levels and prevent voltage fluctuations, which can damage equipment and reduce its lifespan. The National Electrical Code provides comprehensive guidelines for the design and installation of grounding systems. These guidelines cover a wide range of topics, including the selection of grounding electrodes, the sizing of grounding conductors, and the bonding of metallic equipment. Compliance with the National Electrical Code is essential to ensure the safety and reliability of electrical systems. The grounding electrode system, as defined by the National Electrical Code, is the means by which the electrical system is connected to the earth. The grounding electrode system must be capable of safely conducting fault current to the earth and must have sufficiently low impedance to ensure that overcurrent protective devices will operate properly. The National Electrical Code recognizes several types of grounding electrodes, including metal underground water pipes, metal building frames, ground rods, ground plates, and concrete encased electrodes, also known as UFOs. Each type of grounding electrode has its own advantages and disadvantages, and the selection of the appropriate grounding electrode depends on the specific site conditions and the requirements of the electrical system. Metal underground water pipes are generally considered to be the most effective type of grounding electrode, as they provide a large surface area in contact with the earth and typically have low impedance. However, metal underground water pipes are not always available or suitable for use as grounding electrodes, particularly in areas with non-metallic water pipes or where the water pipes are not electrically continuous. Metal building frames can also be used as grounding electrodes, provided that the building frame is effectively grounded and bonded to the electrical system. Ground rods are a common and versatile type of grounding electrode that can be used in a wide range of applications. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to provide a connection to ground. Ground plates are similar to ground rods, but they have a larger surface area and are typically used in areas with high soil resistivity. Concrete encased electrodes are grounding electrodes that are encased in concrete, typically in the foundation of a building. Concrete encased electrodes provide a large surface area in contact with the earth and are often used in areas with high soil resistivity or where other types of grounding electrodes are not practical. The grounding electrode conductor is the conductor that connects the grounding electrode to the electrical system. The grounding electrode conductor must be sized in accordance with the National Electrical Code and must be installed in a manner that protects it from physical damage. The National Electrical Code also requires that the grounding electrode conductor be bonded to all metallic equipment enclosures and raceways to ensure that all metallic parts of the electrical system are at the same potential. Bonding is the process of connecting metallic parts of the electrical system together to create a low impedance path for fault current. Bonding is essential to prevent voltage differences between metallic parts, which can create a shock hazard. The National Electrical Code provides detailed requirements for bonding, including the sizing of bonding conductors and the methods of making bonding connections. In addition to the grounding electrode system and bonding, the National Electrical Code also requires the use of ground fault circuit interrupters, GFCIs, in certain locations to protect against electrical shock. GFCIs are devices that monitor the current flowing in a circuit and detect any imbalance between the hot and neutral conductors. If a ground fault occurs, the GFCI will quickly trip the circuit, preventing electrical shock. GFCIs are required in locations where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. The inspection and testing of grounding systems are essential to ensure that they are properly installed and functioning correctly. Grounding systems should be inspected and tested regularly, particularly after any modifications or repairs to the electrical system. Grounding system testing typically involves measuring the impedance of the grounding system and verifying that all bonding connections are intact. If any problems are found during the inspection or testing, they should be corrected immediately to ensure the safety and reliability of the electrical system. Local amendments or regulations may have additional specific requirements.